Hello and welcome to Tribe Topper. In this video session, you are going to learn about internal energy and specific heat capacity. Let's talk about internal energy first. So, what is the internal energy of a substance? As the name suggests, that means whatever is internally present in a substance. So, because the atoms and molecules they are arranged, they have a typical pattern or configuration, so they have some potential energy due to their configuration, and when the particles vibrate or they move around, they have kinetic energy. So the internal energy will be the total of the potential energy and the random kinetic energy of all the particles present in the substance. So, what do you imagine when you heat a substance? What happens? On heating, these particles they vibrate even more. So, they can move far apart, right? The molecules they move farther, so their potential energy increases, and when they move farther the potential energy increases, and in the motion or in the vibrations the kinetic energy also increases. So that's why we would say that molecules move farther, so the kinetic energy and the potential energy both increase, and when both increase the internal energy also increases. That means on heating a substance you increase its internal energy. But do remember, it's only in a solid, because when we increase we give heat to some solid substance, it will increase the kinetic energy and potential energy of the molecules. But if we talk of a gas, they anyways are very far apart. They do not have any forces between them, right? Because we have learned that intermolecular forces in gases are almost negligible, so they cannot have a potential energy. So all the heat that we give is is going to raise the kinetic energy of the gas. So that's why we would say on heating in a solid you will increase the kinetic and potential energy of the molecules, but in a gas it is just the kinetic energy, because there are no forces between the molecules of a gas. So of course no work is required to pull the molecules apart, and hence no potential energy. Now let's talk about the specific heat capacity. As you all know, when you heat some substance, the temperature of that substance is going to rise. So let's say you take some water in a pan, and in one pan you have 100 grams of water, in another pan you have 500 grams of water. So definitely the 500 grams of pan water would need more heat. And if you need to increase the temperature for one by 10 degrees Celsius and the other pan by 20 degrees Celsius, that will need more heat. So we can say that's the heat capacity to absorb, like how much heat energy is required, that depends on the mass and how much rise we want to cause in the temperature. So therefore Q is generally used to denote the energy, heat energy absorbed or released. So that Q is going to be proportional to the mass, because greater the mass, higher the energy required, and times delta T. That means more the rise in temperature you want, more heat energy will be required. So this leads to, when you remove the proportionality sign, you get Q is equal to M C delta T. The C I have introduced as the constant of proportionality. So when you remove that, it becomes Cm delta T, but it's always more convenient to say it as Q is equal to Mc delta T. What is this C? This C, which I introduced as constant of proportionality, is called the specific heat capacity. And if I have to define specific heat capacity, I will do one thing. C is equal to Q over M delta T. I say if the mass is 1 kilogram and delta T is 1 Kelvin, then C is equal to just Q, and that gives me the definition that we have here, that specific heat capacity of a substance is the energy transferred to 1 kg of a substance causing its temperature to increase by 1 Kelvin. That means if we have 1 kg of a substance and we are increasing its temperature by 1 Kelvin, then whatever amount of the heat energy is required, that is its specific heat capacity. And also from this expression, you get the unit of the specific heat capacity, because C is Q over m delta T, so that will be joules per kg per Kelvin, right? So this is the unit for specific heat capacity. Now let's solve a problem based on this. So we have a question that a metal block of mass 1.5 kilogram loses 20 kilojoules of heat. So let's write down what are the parameters given to us. Mass of the block 1.5 kilograms loses 20 kilojoules of heat. So they have already given us Q, that how much heat energy is lost, 20 into 10 raised to the power 3 joules, because it is kilojoules here. As this happens, its temperature drops from 60 degrees Celsius to 45 degrees Celsius. So what is delta T? The change in temperature is 60 minus 45, that's 15 degrees Celsius. And what is the specific heat capacity of the metal? So all you have to do is write down the given parameters, what is to be calculated, and now we know what's the formula which relates all of them. That's Q is equal to mc delta T. Rearranging the terms, you get C is Q over m delta T. Q is 20 times 10 to the power 3 over m is 1.5 times delta T is 15 degrees Celsius. And solving this, we get 888.9 joules per kg per Kelvin per degree Celsius. So this is our specific heat capacity, right? So all we did is write down the mass, Q and delta T that is given. You should identify that clearly from the question, and then what is to be calculated, just rearrange the terms from the basic formula and you can get your answer. So that's all for this video session. In the next video lesson, you're going to learn about specific latent heat.